Okay, thank you. So the talk is an elaboration of a talk I gave with Chris Vutrick at the Philosophy of Science Association in Atlanta in November. We had 20 minutes to give this talk, so I think I've tried to figure out how to pace it into more like 45 to 50 minutes, but it may still have some of the traces of that. I've put Chris parenthetically, so, to give him credit, but to shield him from any, blame that you may want to lay on the talk today, and the various other people who have, and institutions that have helped us. Oh, I'll write this, there's a bit.ly address here. It's a little s. If anyone wants to download these overheads, you can find them there. The only difference, well, these have the transitions. The only difference between what you'll find online and these is actually that the URL is different, but that should be the correct URL. So the talk is something like, I mean, philosophers I think will be sort of used to this kind of talk, but maybe to say something especially for sort of physicists about what's going on here. It's a sort of something like some physics tourism, a large part of this talk in two ways. One is that I'm going to talk about, I feel kind of embarrassed compared to a lot of the other talks where people have actually produced physics and talked about the physics they've produced. I'm just a visitor in physics, and I'm going to talk about some of the things that have been done by other people. So I'm a tourist in that way. It's also, of course, extremely brief. So what you're going to get here is essentially some postcards from this visit that I've had to this branch of physics. But then at the end, I want to come back and use that to set up some philosophical issues that I think should be interesting to people thinking about cosmology in this way. So that's sort of enough background. The work grew out of the project that Chris and I are the PIs on. Our space and time, well, the general project is the Beyond Spacetime project, and at the moment we're under a Templeton grant for space and time after quantum gravity. So you can find out more about us there. I have a couple of pictures here to, well, actually before I come to the pictures, I say it's our project. The our here, and I mean, isn't just Chris and me. John Doherty's part of the project. Karen's part of the broader Beyond Spacetime project. So, we have other representation here. Is that not going to work? Sorry. Uh-oh. It's going to be a pain if that's... Okay. This is a picture Chris drew, which sort of illustrates, is just in a pictorial way, a spin network from loop quantum gravity that's supposed to constitute some kind of, in some regime, or in some approximate effective way, a classical space-time. That's a picture I drew from a talk I gave recently about how how black holes are modeled in string theory. So these are supposed to be quantum gravity constructions of space-times. And our project was focused on the general idea of emergence, which we heard a lot about from Karen yesterday. Did a really nice job. I don't know if it's exactly clarifying the notion of emergence, but showing just what a kind of complicated notion it is in a really nice way that I think Chris and I took it in a very kind of, I don't know, one-dimensional way, and it's clear that there's a lot of dimensions to what could be said there. So I thought that was very nice. The idea that we were developing in this talk to sort of push these ideas further is, if it's true that classical spacetimes arise just in are somehow built out of or effective descriptions of more fundamental quantum systems, then, and this is a point Daniele has sort of emphasized and mentioned in his talk, there's at least the possibility that there can be something like a transition from some region of the universe which is just not geometric or spatiotemporal at all to one that is. So the possibility of different states or different phases in a very loose sense of a system, at least in principle, raises the possibility that there could be a transition from one of these phases to another. So just like if you think of a collection of atoms, they can have a solid state description if they're forming in a solid phase, but if they were in a liquid, they could have a hydrodynamic description. And there are transitions from the hydrodynamic phase or from the solid phase to the liquid phase as the system melts. Okay, so applying that kind of analogy to quantum gravity. I should mention here a paper that Rudi Vaz, I don't think it ever got published. It was supposed to be in a book, but it's been on the archive for a while, which is a long list of quantum gravity cases where there's or different ways in which space-time could emerge from something non-spatiotemporal. It's sort of a big catalogue of cases one might think about. What else have I got? So there's a lot of reasons for philosophers to be sort of interested in this possibility and this kind of transition. Here's a few of them. Might shed light on what non-spatiotemporal degrees of freedom are. What are the fundamental objects and structures in quantum gravity if they're not spatiotemporal? And how do they form space-time? So, Daniele talked about this in sort of in a synchronic way, like how is it at some time they can form space-time? But this question is, but also thinking about it in a, right, obviously diachronic transition kind of way is another way of looking at that kind of question. You can see from what I've been, the way I was sort of struggling with language there, that there are sort of some interesting philosophical questions here about how are you supposed to think of a transition from the non-spatiotemporal. If you have a state which is, by specification, non-temporal, in what sense does one have a transition? So I'm going to just use that kind of temporal language as I go through the talk. I don't want to kind of have to start the talk with a major reformation of language, but we'll come back to that at the end as a philosophical question to talk about. Right, how can there be changes, befores and afters, processes? Chris and I also, in an earlier paper, raised the possibility of an issue of empirical incoherence for theories of quantum gravity. So I won't say much about that here, but right now, but I'll come back to that at the end. If you know what I'm talking about, then good. I think, right, I'm just going to back up one point. I'm going to talk, the picture, the idea, if there is such a transition, is it's very natural, and this seems to be what most people are thinking, that this transition, from our point of view in the spatiotemporal universe that we live in at the moment, this is what replaces the Big Bang in quantum gravity. I'm going to be a little sloppy in my language here. I think the Big Bang is supposed to really refer to the initial singularity in kind of classical models of space-time. And we're going to be thinking about inserting something quantum at the Big Bang, but not literally at that point. In some sense, it's going to be smeared out. So I'm going to be a little loose on my language there. If I say things like at the Big Bang, I don't mean just where the singularity is. It's going to kick in some sort of smeared way. I have to say smeared because if it's not temporal, I can't say that it's temporally extended, but in some sort of sense. Okay. And to get through to these ideas, I'm going to talk about 3 examples, depending on how time goes. The main example I want to talk about is some models in string cosmology that are related to things that Robert said on Monday. I will talk a little bit about loop quantum cosmology, which is the part of the project Chris was working on. So I'm going to summarize some of the things he said. And Francesca mentioned this, I guess that was Monday 2, and if there's time, I might talk about Geometrogenesis, which Daniela also mentioned on Monday. But let's see where we get to. Okay, so in case you want to see the logical organization of the talk, it's pretty straightforward. We've done the introduction, the basic idea of transition, perhaps from something not fully spatiotemporal to something spatiotemporal. And now the examples, and then we'll have some discussion. And actually, there's one more thing I should warn you about. We're going to look at these different examples, and there's going to be kind of apparent quite quickly that there are sort of degrees of how much degrees in which they lack fully spatiotemporal notions or structures. Some of them more so than others, and indeed that's one of the issues that we'll return to right at the end. I'm generally going to say non-spatiotemporal. That's probably too strong in most of these cases. What I should say is not fully spatiotemporal or less than fully spatiotemporal, but I think you'll get a bit bored if I have to say that every time that I'm talking about this. So if you hear non, hear that in a rather loose way, please. Okay, on to the string cosmology. So I think for each of the case examples, the cases, I'm going to give you a reference that are at the end and in the slides. These are really to sort of secondary review type pieces that contain the references to the primary literature. So this is a model, a sort of system that Gasparini and Veneziano worked on in the early 2000s, I think is about, and it's about right. And here's a very nice textbook that deals with these issues, and indeed talks about some of the issues Robert was talking about as well. So I've been talking about string theory long enough that I sometimes feel that everybody else in the philosophical community must know everything about what's going on, but I know that's not quite true. So let me just back up a little bit and make sure everybody's on the sort of the same page here. So string theory, obviously a theory of strings. Robert had the model. I should have borrowed your elastic band, but that's the thing. I'm sure it was vivid, imprinted on people's memories vividly enough that they will remember. Okay, so here's my rubber band, and here's one thing a string might do. It sort of propagates in time as a circle, then it splits. This is supposed to be, if you looked from the top, you'd see this was a torus with two open ends, two holes in it. Splits into two and then joins on again. So that's basically what you need to know about strings, that they're physically, spatially circles, and they can split and join, and then you can just think about everything you can do with that. They have some physics, and here's the, So if you want to describe them, of course what you need to do is to say for each point on the string, and there would be coordinates, two-dimensional coordinates on the string world sheet, sort of label points, but each point has a position in target space, some background space in which they're, space-time in which they're living. So this is actually supposed to be a 4-vector, I guess. I maybe shouldn't have done it that way. Okay, so to sort of describe the state of a string at a moment, you need to just to describe the trajectory of the string, it's a world sheet, you just want to say where each point is in space-time. And then that tells you the state of the string. But at least formally, in some ways conceptually, one then sort of flips this sort of picture around and now focuses on the world sheet, two-dimensional thing, as if it were a space-time. It's a very useful way to kind of be thinking about it. And then here's, it's actually not a sigma, the action that I'm going to talk about in this model. So we'll describe the motions of the string. This L sub s is the string length, so it's a characteristic length of the theory, which is generally taken to be a couple of orders magnitude bigger than the Planck length, so very small. As I said, it's an action for the world sheet, so we're going to integrate over the world sheet. One of the features is there's not only a metric on the space-time in which the string lives, string theory also involves a two-dimensional metric that's added onto the string itself that has to agree causally with the target space metric, but is not the restriction of the target space metric to the world sheet. For that reason, it's actually not really a physical parameter. And so there's a conformal symmetry associated with this auxiliary metric. The terms inside, so in here, there's a sort of contraction involved. I sort of haven't written the metrics in explicitly, but you can see I had to do a sort of contraction between, there's two derivatives here. They're derivatives of the external space-time coordinates with respect to coordinates of the world sheet itself. There's a contraction with respect to the big space-time metric, which goes with these mu's. So g mu nu is in here. There's a contraction with respect to the coordinates, the world sheet coordinates. So this auxiliary metric is also in here. There's a sort of double contraction. So normally that's the sort of bosonic string action. But you can add other fields to it. And one interesting thing to do is add a scalar field that's coupled to, this R is the scalar curvature of the string, not of the target space. So it's coupled to the geometry of the string. From the point of view of the string, what we have is a two-dimensional space-time, and these are really d-component vector fields that live on the string. So this is quantum field theory from the point of view of the string world sheet.
Background's completely arbitrary?
Yeah. No. I mean, to start with, yeah, right. I mean, but this is the answer to your question. It's right here. And I'm sure you know what the answer is. Okay. So, right, as Enrique asks, I can in principle, my g mu nu that's doing the contraction here could sort of, seems like it could be anything. But there's an important story. As I mentioned, because this action involves a metric that has no physical significance beyond its the conformal structure, which it has from the background, there's a conformal symmetry in this action. At the classical level, I mean, it's just a mathematical result that this has conformal symmetry. So let me make sure I'm getting this. I'm going to tell the story in the right points. Right. So essentially what I've written down here is a classical action for the string. Quantize, going to take this as take a path integral of this and pretend, imagine that it's a well-defined object and everything is hunky-dory with that. It's going to need renormalization. There's going to be a renormalization group analysis that's going to produce beta functions for the field, for the objects that are in here. They're going to be beta functions that are running with respect to distance or scales on the world sheet. But again, the conformal symmetry means there can't be any variation with respect to those. The beta functions have to vanish. And that then places constraints on the background fields, on the g mu nu and on the scalar field that I put in there. And then they look like, those constraints then can be expressed as an action that relates those background fields, g and this scalar field. I didn't write over here, I could put in other kinds of background fields, and then there would be sort of terms for them as well.
So you think of the conformal transformation as acting on the world sheet metric,
yeah,
not on the background
Right. There's not conformal, right, there's not target space conformal symmetry. All right, I gave a little more detail than was perhaps necessary. There is a classical Weyl invariance, sort of for the reason that I gave. It's required then that there be one at the quantum level, and requiring that requires then this be an action that relates the background fields that the string is living in. So when you have an action like this, the phi field turns out to be called a dilaton field. And so, okay, here's the action that one has. So some comments on that. This is a result that I kind of sketched in terms of beta functions that one gets to lowest order. Well, to first order, it's not exactly to zero order. I think I say something wrong in a later slide. It's a lowest order. In string theory, there's a double perturbation series that you take. One is sort of when you treat this as a quantum field, you expand in, think of this as a field on a given world sheet, and you have a quantum field for that, an expansion for that, and you can see, well, you can't quite see, but the first expansion for a given world sheet is this parameter in which you're expanding is something like the string length times the curvature. So the string length is fixed, but if the curvature blows up, then this expansion is not going to work anymore. You also have to sum over all the topologies of the world sheet that you can have, so basically all the different numbers of holes that you can have, and the number of holes, the more holes there are, the higher and it is in perturbation series, and it's higher in powers of the string coupling. So if the string coupling were to blow up, you'd also lose perturbation theory. What I'm not going to be able to sort of show you explicitly here is, in fact, well, I'll come back to that. This is also, okay, I'm going to come back. There is a way in which that can blow up. So how are we supposed to think about what's going on here? This sort of came up in Karen's talk, and we didn't get to sort of talk about it then. The background fields, and the ones that I've sort of put in here is that's sort of hidden here, the G mu nu, and this dilaton scalar field phi that you can see over there. The way I wrote them down, it's as if they're independent sort of objects that are given, and then you put the string into them. That's the party line on this, I would say. So the thing you're taught in the textbooks, and this is actually what this CF means. We didn't show this, we just talked about it. We have a longer discussion about it, and particularly sort of this point. That's not the way to think about them in string theory. These fields, any of the fields that you put into the string, you will find excitations of the string that correspond to the quanta of these fields. And so those background fields you're supposed to think of in some way as classical approximations, hence coherent states built of those string modes. Okay, so I sort of have a picture of that here. So if you start, this is supposed to be a classical field, and you can sort of see it in space-time. First step, you think of it in quantum field terms, and those little anteg things are supposed to be quanta of the quantum field that are building up that state. So this is sort of my picture of a coherent state, because I want this to be a classical field. And if you look inside each of those quanta, you'll see that it's an excitation on the string. So one point it's maybe worth making is there is a move from strings to quantum fields here that we'll sort of see come up again. You don't want coherence. You don't want to take a single string and it's got quantum excitations. You don't want to build up a coherent state on the string, because as you excite a string more, you don't get more particles. You just get different particles. What I want is a superposition of. I want a whole load of strings, all of which represent gravitons collectively in a coherent state. So this is kind of moving beyond what you have a lot of immediate access to in string theory, I'd say. Okay. So to go back to Enrique's question, no, it's not arbitrary which one you put in. They have to satisfy this action. There's a certain amount of arbitrariness when you think about what's going on. Let me just leave that one. Yeah, okay. We're going to run out of time if I don't do that. Okay, so that's just the sort of nature of this result. But we look at this action, and if you can call up to memory what the Einstein-Hilbert action looks like, this looks like the Einstein-Hilbert action, except the gravitational interaction strength is we have R here, right? So reading off the gravitational interaction strength, we actually see we have an exponent of the dilaton scaled by powers of the string length. This is really the gravitational interaction strength, and so the dilaton has this weird effect that it can change the gravity. It actually determines what the gravitational gravitational interaction strength is. As I said, I'm not going to show it but it's also the case that the string coupling is a function of the dilaton. So I've got a theory where the dilaton can vary, and that can vary the coupling strengths in the theory. So that's going to be an important part of what's going on, because we're going to need to track what happens to the dilaton. So looking ahead, large curvature is going to kill the perturbative result in certain regimes. So are certain values of the dilaton.
Sorry, quick question. You haven't mentioned compactification. I came a little bit late, but is there a reason you didn't talk about the compactification?
I didn't have anything to say about it that was relevant here. Did you have something?
No, but I guess, usually the conformal invariance requires being in 11 dimensions, and then you have to compactify.
Oh, yeah. No, that's right.
And then that gives you many more degrees of freedom on how you compactify, right? So you have many more things than just what you have.
Yeah, I mean, this is bosonic, so it's 26 dimensions, in fact.
26 dimensions. So you have to compactify 20. So because that was my point, is that in doing that, there are many more degrees of freedom that are introduced, which are basically all the geometric degrees of freedom of the compact dimensions.
So now I have another reason not to bring it up, is so that I don't stir up trouble. Okay, but Robert gave us a kind of answer, a potential answer to this question, I think, on Monday with the string gas cosmology is.
Sure.
Do something to address this, right?
Yeah.
Yeah, I'm afraid I'm working at a much less subtle level. Okay, if you like, you could. I just put these up for completeness. I'm going to give you simpler versions of these, but we have an action, so you can minimize with respect to the metric, and you get, again, something that looks like an Einstein field equation with terms for the dilaton, plus you can see instead of G, we have, again, the powers of the dilaton, and then, of course, there's an equation for the dilaton field as well. Okay, so moving on to solving these, do the same thing. One of the things that's obvious to do to try and make things simpler. Okay, well, we're going to just look at 4 dimensions. So I guess we're imagining that the other dimensions are just tucked away, and then we're not going to worry about them. And just look for solutions with a spatially homogeneous, isotropic, flat spacetime, and we'll get rid of matter as well, but allow the geometry to be time dependent. So look for solutions with where G mu looks like this. So the parameter is A, something like the scale of the universe, the size of the universe. Although I'm not assuming these dimensions are compact. They could be this. We could be talking about infinite universes. So it's just a bit of math. With those assumptions, the previous equations, the first one entails these 2 equations, basically for the spatial and temporal parts of the metric, And this is the equation that comes from the dilaton dynamics. And it's useful to introduce the Hubble parameter. And I'm also going to pick units where the string length stops showing up anymore. And one gets equations like this. Okay, one point to make sort of fairly quickly. It's quite easy to see these equations have a couple of interesting symmetries. Well, they're time reversal invariant. They also have this scale inversion. So if you've thought about string theory and you know anything about T-duality, there's a duality where you can flip the radius of the universe for its inverse. There's something similar to that where you can flip the scale. So this is something like a T-duality that doesn't require a compact dimension, as long as you also rescale or redefine the dilaton. There'll be an equation for a symmetry for that as well. And in case you're worrying, this isn't just an artifact of the simplification that's made here. These are full symmetries of the other equations. So that's sort of interesting if, like me, you've thought about T-duality. It's a sort of generalization of that idea that's kind of interesting. For our purposes, it sort of shows something about what happens when you have a dilaton, how it relates to the metrical properties. There are a lot of variations you can make in the metric as long as you make compensating variations in the dilaton. Okay. These, for our purpose, so these are kind of cool, but for our purposes, they'll just be a shortcut for finding solutions to these equations. Okay. So there's a sort of t greater than 0 solution, and it looks like this. You can easily plug those into the equations and see that they work out. So I've color-coded them to help, I hope to help make this sort of more readable. So this is the scale of the universe, sort of the length, and you can see it's growing. We have an always expanding universe. But if you take the second derivative, it's negative, so it's decelerating. So that's supposed to be what's pictured there. So that's a Friedman-Robertson-Walker metric spacetime without a cosmological constant. Look at now moving on to the red. This should be a goes to rather than an equals, I think. You'll see the Hubble parameter blows up as time goes to 0. Which sort of tracks the curvature. So there is a curvature singularity, and there's the form of the dilaton. It goes like the log of the time, and so the string coupling will go to 0. Actually, sorry, I should have said it explicitly. This is the dependence of the string coupling on the dilaton, and so it's actually going to go to 0 at early times in the universe. So this has some features that, well, there's no inflation, but in a sense sort of looks like ways people have thought our universe might look. You can now quite quickly just apply the time inversion symmetries and the scale inversion, time reversal and scale inversion symmetries to see that there must be a parallel set of solutions for negative times. Okay, we have A is actually growing from 0 and expanding because times they're all negative. Okay, we have these solutions. So this is an expanding universe, but it's actually, if you take the second derivative now, as you go forwards in time from larger negative to smaller negative times, we get a positive acceleration. So the sort of mirror solution is an inflating universe. This is negative, of course, so it also blows up in the scale as time goes to 0. Okay, there's the Hubble parameter. That again is going to blow up as time goes to negative 0. So we're going to get again a curvature singularity. This time we get the string coupling actually blows up as you go to negative 0. I'll also just mention, if you look at these, you'll also see time goes to minus infinity. There's no singularity. There's nothing like a Big Bang. In fact, you have just like a very nice, nothing much happening at all. curvature disappears, coupling disappears, it's all nice and quiescent, and then this all happens after. Why does it why is that happening? It's the presence of the dilaton that's making this happen. Okay, so we have those two solutions that are defined after zero and before zero. Again, these solutions hold, as we saw, to lowest order. They assume small string coupling. They assume small curvature. And exactly what we've just seen is at around zero, those are the assumptions that fail. So our approximation should be good, well away from zero, but bad around zero. But drawing them like this, I think you would think, wow, I think there's a big bang here and there's a big bang, so whatever, it's not a crunch, it's sort of banging the other way because it's still getting bigger. Can't these somehow be joined together to make an infinite universe? Okay. So that would be kind of nice. So, can we put them together at the region where they, at the t equals 0 region? Okay. So, obviously that doesn't make sense from a classical point of view. They're singular there, so how are you supposed to join them together? There's discontinuities in the scale of the universe there. So they can't literally just be stuck together like that. But, as I've been sort of emphasizing, and hopefully you picked up on the foreshadowing, I said zero, they're first order equations. The equations are invalid. They're going to break down around this region anyway. So if there's any joining to be done, it's going to have to be of a quantum nature, a quantum stringy nature. We're going to see the strings, we're going to see the quantum mechanics of the strings. So that's a nice question now is, well, does string theory let them join? So unfortunately, unless things have changed recently, I don't think anyone knows. It's too hard to know exactly what's happening here. So instead, what I can do is sketch some possibilities about what's happening. There's sort of other pictures one might take, but here's the sort of main three things that you could sort of think of in the context that I've been describing. And again, Gasparini talks about this in more detail. So we know the thing is breaking down in two ways. Maybe the curvature related part of the perturbation theory is what sort of breaks down first, and once one includes corrections from that, there'll be a way to smooth them out. Okay, actually I should put, one possibility is no, they don't join, but let's assume they do, and how might that actually happen? That's the question I'm interested in. There's curvature corrections, then in a sense, you're not seeing, in a way I'll explain in a minute, the full quantum theory, quantum string theory. And so what you're going to get is something more like a modified version of GR that smooths out the singularity. There'll be other terms in my field equations that prevents there being a singularity and around t equals 0. So it'll look like the equations we have at early and late times, but not around t equals 0. Going back to the question of emergence, that's sort of the least interesting possibility. Second possibility, sort of more interesting, is that the string coupling corrections become important. They're the ones that need to be looked at first. That's kind of interesting because when we have that's exactly what allows the strings to join, in this picture, to split and join. And if you're thinking of those like as you should in the party line as Feynman diagrams, what you're talking about is something like annihilation and creation of strings, something like a field theory where the strings are the quanta of the field. And that's a different regime from what you're really now looking at the full quantum mechanical nature of string theory. So that's really taking us to a stronger kind of like quantum gravity that you really see. Not just sort of quantum mechanical corrections to classical gravity, but something more like full quantum theory of gravity. The other possibility is you can't do, neither of these alone is enough. And both kinds of approximation break down, and that presumably is the regime where the notorious M theory lives, and maybe that is non-spatiotemporal. Since we don't know what it is, no one really knows. I should say, in this place here is more or less where, as I understand it, the string gas cosmology lives. That's one of the things that can happen in here that Robert talked about on Monday. So there's sort of three things that can happen of increasing kind of non-spatiotemporality. Okay. Of course, we'd like to know more about exactly what's happening. So I want to spend most of the time on the discussion. So I think the two other examples I'll be pretty quick about. One can do something, so loop quantum whoa. Sorry, I know what to do. I pressed the wrong button. There we go. Interesting. Loop quantum cosmology does pretty similar to what I just talked about, as I understand it, but from the loop quantum gravity point of view. It's actually, yeah, sort of very similar. I think the one issue I wanted to raise here, you end up with a sort of another sort of Big Bang smoothing kind of region in these models. One possibility, so this is a recent, perhaps forthcoming paper that I think we're going to publish in an anthology that we're editing. One of the things, it comes from earlier than that, but it's discussed there, is that what's happening in this region. Can you tell me at the end that I'm wrong about this? And okay. There is this idea that there might be this signature change of the metric around. Am I wrong about what he's saying, or is he wrong?
I think that
Both.
there could be developments.
Okay. All I want to put on the table is the possibility that one of the things that happens in a sort of Big Bang region is that there's a signature change. You have a region where the emergent geometry, the derived geometry, is fully spatial and not spatiotemporal. If you don't like this example, I mean, the no boundary Hawking-Hartle has a similar kind of sort of case. Yeah, okay. Which people did talk about back in the day a little bit. Okay, there's another point here that's really Chris's point. One way of describing this universe is one that sort of starts infinite and crunches down and then, I guess, bounces out. Chris wants us to think about this as a single Big Bang with two universes that develop in opposite temporal directions. All right. This really, I think, is the sort of cleanest sort of example of that I know of that we have of what's going on. This is, in a sense, sort of recap of some of the things Daniela said, although I'm going to talk about, though it's supposed to illustrate the Geometrogenesis, as he calls it, part of the story. I'm going to go very quickly through this too. But if you remember, at the heart of the story of how to derive spacetime is from the group field theory, these tetrahedra. It's possible to define in group field theoretic terms a metric at the sort of tip of each tetrahedron. And the result that they have is, if you now think of space as sort of full, but better kind of constituted maybe by a whole load of these tetrahedra, if you want a homogeneous metric, then you need a coherent state of these tetrahedra. That's just supposed to be reminding you what Daniela said on Monday. And then one can get dynamics as well by applying quantum fluid mechanics to that. So this is my way of putting things, but this is Daniela's suggestion was on the slide, is But if they're not in a coherent state, then it seems like we're maybe not going to be getting any space-time. If these tetrahedra aren't condensed in the right way, there's no space-time. So there's states without space-time. He's shown there are states with space-time. This brings out the idea of a transition. Okay. So we talked about the string cosmology, and very quickly I talked about loop quantum cosmology, which was Chris's part of the project, of the talk. And then there's joint parts as well. And let's move on to some discussion. Okay. I'll try and leave 5 minutes at the end for questions, if that's, I don't know, how long was it supposed to be 5 to 10 for questions? I'll be done in time, I think. I have four issues that I want to put up that are sort of raised by these examples, some that people have talked about, and I'm not sure I have any dramatic philosophical conclusions to give. I mean, I assume quite a bit of this is new to people, and it's things I've only been thinking about some of this for a little while. So I want to put the questions and maybe sketch some different directions one might take them. It's also the case that I've been thinking, people have been saying things at the meeting that are kind of relevant to what I'm going to say here, and so my thinking has really been even changing in the last few days. So I should have put the reference in here. On the group field theory talk slide, there was a reference to Daniela. It's actually a video of a lecture he gave us, and one day will be a paper that he'll give us. So. Okay, where he describes the Geometrogenesis based on earlier formal work, and also discusses these levels of emergence of space-time geometry, which I think is a kind of nice scheme for starting to think about how to make some important distinctions. All I wanted to do using the examples I brought up was to just point out some other how the scheme might be used and how it might be refined. His levels go something like, okay, so the lowest level, we're still perfectly classical. Maybe we've modified GR, but it's still classical spacetimes. The lowest level, and I'm going to put them in my terms, is just a sort of straightforward quantization of gravity, where all you really have in some way is just superpositions of classical gravitational states. Nothing very sort of dramatic or subtle has happened. So this is just sort of, naive quantum gravity. I'm going to collapse more or less two levels into one here, because I think just for sort of simplicity here. The next sort of thing is, well, look, what if the theory's degrees of freedom, basic elements are non-spatiotemporal atoms in some way, then can they make space-time states? Do they always make space-time states? Do they sometimes make space-time states? But there's the pre-spatiotemporality and the question of then how do you get space-time out of that? And then the sort of strongest level, these are sort of lowest to highest, but they're upside down because that's how we write. This is the lowest level. At the highest level, there is this question of transition. If there are non-spatiotemporal and spatiotemporal states, can there be something like a transition from one to the other? So the scale is something to do with how hard it is to conceptually and formally recover space-time, model of the universe from this kind of theory. So just a couple of comments thinking about string theory, so we saw two options there about what might be happening in my model that I discussed here. one can sort of imagine different models. Somewhere you need M theory in the middle there, which seem to kind of come to the highest level if M theory is really non-spatiotemporal. Though, as I said, we don't know what M theory is, so there's no way to say whether its atoms really are non-spatiotemporal or not. But there's also a possibility that we just have quantum corrections, in which case string theory, this model would be something more like just at this first level. So the first point I wanted to make was that this isn't a classification maybe of theories, but of sort of models of the theory perhaps. These are supposed to be friendly kind of amendments. In loop quantum gravity, so loop quantum cosmology, putting aside Francesca's head shaking, we have a quantum region here, but there seem to be two distinguishable sort of possibilities about what's going on. One is without signature change and one is with signature change. And those seem to be maybe both somehow at the superposition of quantum gravity level, but would require sort of a further distinction at that level. Okay, so one issue to bring up then is how to sort of characterize different kinds of emergence. Empirical incoherence. Chris and I, in an earlier paper, raised the idea that's commonly held that all observations, including observations of the results of experiments that you perform, so even when you're sort of interacting with the world, require there to be something that is, in a very broad sense, localized, that it's somewhere in space and time. If that's the case, a theory that predicts there sort of is no space and time seems to predict that, or if it really said there was no such thing, is predicting that there can be no observations, no experiments, and so undermines, it is predicting that it has no empirical consequences, that it can't be empirically confirmed, and that makes it, I think in Jeff Barrett's terms, sort of empirically incoherent. That couldn't be a theory we could have empirical reasons to hold. Of course, what one expects, what should happen then in a theory in which which was non-spatiotemporal, is that there are effective, approximate, emergent space-time structures, and experimental results are referred to those. But in the strongest kind of cases talked about here, it does predict that there are regions of the universe where nothing can be directly observed there. So there is no direct empirical evidence for that region, for what's going on in that region, by construction. Of course, the answer is going to have to be that what's the existence of such regions is inferred from experiments and observations in the regions in which things are geometrical, in the geometrical regions. But just a suggestion for people to think about. These regions are unobservable in a very strong sense. It's not just that they're sort of too small or too far away. They're just the kinds of things in which observation is just not possible. So that may have some bearing on how evidential current experiments are for the inference to those regions. Of course, there may be once you allow that there are states that are non-spatiotemporal, there may be possible worlds according to a theory which do have can't be tested empirically because there is no space-time in any of that universe. And there's quite a lot packed into this. What are the direct, indirect? So what are the indirect observations the inference is going to involve? Well, Robert talked about looking at the cosmic microwave background for evidence of what happened in the early universe. There's a prediction from the string gas cosmology. Now, as I said, that seems to be something like a quantum. You're only in the quantum realm there. You're not fully down here. But one would imagine something similar being the story if one was thinking about an early universe which really had a non-spatiotemporal characterization. So maybe I'll just put this to the philosophers who probably know what I'm talking about. David Alberts argued that the ability to understand what a trace of the past says requires us to have some view about what happened earlier, about a past hypothesis. There's no past hypothesis if there's no time earlier. Okay, there's lots of things that one could say to work on that, but let me just put it in that crude way. Okay, so maybe it's not going to be 5 minutes because I want to put... So I'm not quite sure, Simon asked this question on Monday to Daniela, and I'm not quite sure how it got resolved, and I'm not sure if it's the same question, but it was something I wanted to talk about anyhow. So think about the strongest level. I've tried to sketch some theories that may reach this level, where there is something like a transition from a non-spatiotemporal phase to a spatiotemporal phase, and come to the question of what it is to say that there's a transition. So a transition, okay, I'm going to break it down, and I've written on the board over there how I want to break it down. A transition seems, well, on the face of it, you might think requires a sort of a change from some earlier state to some later state, and exactly that's what isn't going to be possible if the earlier state is sort of atemporal, if there's no time at the earlier state. So how should one sort of be thinking about that? Well, so one thing, so I think that, okay, I'm going to say something. One sort of thing one could say to try and think about what's happening at this transition, and then I'm going to talk a bit about what I think it's really sort of pointing to. If we're thinking about a theory in which time is effective or emergent, then in particular direction of time is an effective or emergent notion, and so when we want to describe what's happening at the fundamental level, in terms of the atoms that compose time, it is not necessary to talk about in that more, that higher level emergent way. In fact, it may be impossible, it may be inappropriate. Given that, there's a certain way of thinking about this problem where you're worrying about, well, look, there's just sort of this atemporal mush, and suddenly there's time. You might feel more comfortable thinking, okay, I shouldn't be trying to think about this in fully kind of emergent, fully temporal terms, because those are just effective in this story. But maybe I can use some of the concepts to do that. If you're willing to do that, I would suggest around the Big Bang, putting aside the notion of direction and thinking in terms of, I'm not suggesting running the whole universe backwards, but think right around the Big Bang in reverse and think about what's happening, even though this is something that's happened earlier than us, as a kind of freeze of going from the spatiotemporal to the non-spatiotemporal. There's a kind of freezing out of time or a dissolving of time. Okay, so in the first place, there's something kind of, I find sort of psychologically more comfortable about, time comes from nowhere seems very problematic, time sort of just dissipating at some point. Okay. Now, I'm not sure that that has like more than sort of some kind of psychological comfort for me, but I think what I think's going on in sort of talking about that story is to try and break down the notion of transition into these 5 things. So one thing you might be worried about is like you have a very strong notion of sort of what's happening in time, that one state literally kind of produces another in some heavy metaphysical sense. So Tim Maudlin's not here, so I doubt anybody here is sort of thinking in that way. So we don't want to have, that seems something one has good reasons to sort of give up kind of earlier, just in the classical case. Okay, so forget that one state is in some way, literally, directedly productive of a later state.
Sorry, we have about 0 minutes left.
Yeah, that's okay. 40 seconds. Okay. But it seems to me, again, at the classical level, if you have physics that's time reversal symmetric, we don't really care whether it's already good reasons not to care that a transition could go one way as one way as the other just as well. So maybe even at the classical level of sort of microphysics, if you have time reversal symmetric physics, all one really wants to make sense of what's happening in a process is temporally ordered states. So what I'm suggesting is, even the case that I've just sort of described, you don't even really need the beginning and the before and the end states to be temporally ordered. It's sort of enough that one of them is temporal and the other one is sort of the limit of some kind of process in which time is itself dissolving. So I think this is kind of where I just came to. But what does still seem kind of necessary is there's some sense in which it's... I think I put the question to this way on Monday as well. I'm just sort of imagining all of phase space and sort of all the continuous trajectories. I mean, I suppose it's got enough structure so I can think of all the continuous trajectories through it. What is it that makes some of those trajectories physical ones and others not? You know, if there's no time. So what is the dynamics, you know, what's going to replace something like dynamics if there's no time? And I haven't said anything kind of about that, really. Okay. Yeah. That's fine. I'm done. That's it.
One question. Wow, that's a lot of pressure. So you were talking about this solving of time. Couldn't you think of it in the nearest picture? If you think about time being relational with respect to some other field phi, let's say, then you are thinking about it in terms of, look, there's some configurations in which these phi's align so that you can make up a certain notion of time. And there's some other configurations in which I'm being pictorial here, in which they don't align, so there is no notion of coherent time. So it's just a matter of places in this configuration space.
So I think I'm just going to repeat back what because I kind of asked Danielle some of this like on Monday as well. So but the phi field that you introduced to do something like that, right, isn't a clock in the non-geometric state, right? So you need to find something else that does something like that, right?
It would be a bit of like the picture you suggested. So in the geometric phase, so you have some degree of freedom that behaves nicely to the time. But the question is, okay, you go towards the non-geometric phase, you keep following backward this time flow. At some point, the same degree of freedom ceases to be a good clock, and so you simply have no notion of time and space. But that also means that you can't really characterize the transition itself.
Well, it's fuzzy. It's a fuzzy transition. At some, it's not a demarcation, but at some point you can say, oh, now you have more or less something that characterizes.
Yeah, but you fail to be able to follow up on that in the non-geometric phase. So it's really more.
You want a clock that works through both phases.
It's a physical regime where there's simply no notion of time, and there is a transition line more or less sharp, in which one of the variables, one of the degrees of freedom, starts behaving nicely enough to be called time.
But why do you think it's a sharp tree? That's what it is.
Well, it depends on the nature of the phase transition.
Yeah, right. Okay, I see.
It can be sharp or not. It can be continuous, discontinuous, all sorts of problems. So that becomes model dependent. But the point is that whatever you were using to call time to use as a clock may fail to behave appropriately in the other phase.
Sure.
There you just have no notion.
I think, I mean, should maybe talk more about this in the longer discussion as well, but I think that's kind of what I'm getting at here.
Yeah, okay, so let's have a break and thanks.
Sure.